And I have to apologize for my voice. I'm a little congested today. I'm getting over a sickness. I think it sounds worse than it actually is, but I'm just going to sound like this today. So. Okay, we left off on Wednesday talking about the normal distribution. Okay, so I hope you guys have your normal reference tables. If not, go ahead and pull those out. And we'll try a problem. We'll say blood pressure. And we'll say diastolic. I don't know how to spell it. So this is, when you get your blood pressure reading, it's like 120/80 or something. Diastolic would be the 80, okay? We'll say diastolic blood pressure follows a normal distribution with a mean of, I'm just making up numbers, 73 and a standard deviation of 10. Okay. So this will be your first question. Let me just check some values here. Okay, so I'm going to ask what proportion of people have blood pressures lower than 80? So again, we're saying blood pressure follows a normal distribution with a mean of 73 and a standard deviation of 10. Hoping this system fires up. Question? I'm pretty sure the correct answer choice is available. I'll double check. Huh? It's not? It's not available. Did I mess up? Oh, Yeah, I guess. All right, my bad. I'll change this to 79. Lower than 79. My apologies. Okay. So I'm sorry. Okay. Did we all get our answers in? All right. Just I'm going to click stop here. And the correct answer choice is B. Okay. This does bring up an interesting point. When we color in our... Okay. This never works the way I want it to. So we turn 79 into a z-score. So the z-score for 79 will be okay, and then we look that up in the table, and we find that the area to the left So there's our answer. This does bring up an interesting point, is that because the normal distribution is continuous, oops, hang on a second. This is stats. Because it's continuous, asking what proportion of people have blood pressures lower than 79 is equivalent to asking what percentage or what proportion of people have blood pressures lower than, less than, or equal to 79. So let me just say this, okay? So the probability that blood pressure is less than 79, this is exactly equal to the probability that blood pressure is less than or equal to 79. Okay, so and that's because the normal distribution is continuous. Okay. For discrete distributions, the answers will be different. Okay. Okay, just want to make sure we're okay with this before we move on. Okay, we can. So again, we'll say blood pressure, normal distribution, mean of 73, standard deviation 10. And then I could ask, we'll put 79 over here and 70 over here. And we can ask the question, what percent or what proportion okay. And so the way we're going to get this answer is we're going to split it up into a couple pieces. We're going to say, well, I'm interested in this area right here. We're going to say this is equal to, let's see if I can color this in. Minus that piece. If I could just, all right. And so we're saying this green area here is going to be equal to this orange minus this blue piece, okay? And so the cutoff here is at 73, and the cutoff here is, sorry, not 73. The cutoff over here is at 79, and the cutoff over here is at 70, okay? So all we have to do is we find the area to the left of 79, and then we subtract off the area to the left of 70. And then we'll be left with the area in between 70 and 79, okay? All right, so why don't you guys go ahead and try that out. And let me see if I can... I hope I have the correct answer available this time.
Yeah.
Yeah. Was that? No. I'm a mess today, aren't I? Between 70 and 79. All right, do we have our answers? Let's get our clicks in. All right, just a couple more seconds here. All right, we'll hit stop. Okay, and indeed, D is the correct answer. Okay, so the way to solve this, again, we're gonna take the area to the left of 79. We had already done this from the previous problem. We said z is equal to 79 minus 73 divided by 10. We get a z-score of 0.6, and the area to the left is 0.7257. And then over here, we find the z-score. 70 minus 73 divided by 10, we get a z-score of negative 0.3. And we find that the area to the left of negative 0.3 is 0.3821. Okay? So this is not the area that I'm looking for. I want this area in between 70 and 79. And so I'm going to take the difference between these two values. Okay? So the area between so we get 0.3436, and that is going to be our answer choice here. Okay, sometimes students will take the difference between the z-score, and they'll say the z-score between 70 and 79 is 1, and that's not going to work out. Okay. All right. So far, so good. Okay, this time we'll try something a little different. Same idea. Okay, and then so this time we'll say IQ scores come from a normal distribution of 0, with a mean of 100 and a standard deviation of 15. Okay. And then we'll say, what is the score of someone in the 90th percentile? Okay. 90th percentile means that 90% of people have IQs lower than the score. So you're trying to find the score where 90% of people have scores lower. Are we doing okay? Do we have questions? Okay, so to solve this, we want to know, what is the score that goes here? Okay, I'm gonna go ahead and click stop here. So if you haven't clicked your button, click your button here. So we want to know, what is the score here, so that if I were to color this in, the area colored, this is 90%. Okay, so we want 0.9 right here. Okay, and so we're going to go to our table, and we're going to look for 0.9 in the area. So the area closest to 0.9. And I think we find 0.9003. And this corresponds to the row 1.2 and the column 0.08. So in the normal table, if we look, or I'm sorry, 0.8997. 0.8997. Okay, so we have a value very close to 90%. Not exactly, but 0.8997. That's pretty close to 90%, and that's a z-score of 1.28. So we have this z is equal to 1.28. Okay. Yes, question. Where did I get what? 0.08. So I'm finding in my table, I'm looking for the area closest to 90%, and I have 0.8997 right here. Is that okay? So when I look at this, let me just zoom in at this table here. So I have this is the number I'm finding, right? 0.8997. You guys see that? Okay, what is the row that it's in? It's in the row 1.2. And what is the column it's in? It's in the column 0.08. Okay? So we're going to put those two together, 1.2 and 0.08, and those two combine to make 1.28. Is that okay? So again, we're looking for the value closest to 90%. This is not exactly 90%, but it's pretty close to it. 0.8997, okay? And that's in the row 1.2 and the column 0.08 to make a combined 1.28. Yes, question?
Is that the answer to the clicker question?
That's not the answer to the clicker question, okay? So our z-score is 1.28. Just want to make sure that's okay with everybody. Z is 1.28, okay? And we want to turn that 1.28 into a IQ score, okay? So the z-score, if you recall what a z-score means, this is the number of standard deviations we are away from the mean. Okay, so this person's z-score is 1.28 standard deviations above the mean, okay? So the mean is 100. So the IQ is going to be 100, the mean is 100, and this person is 1.28 standard deviation. So we're going to do 1.28 times the standard deviation of 15. This turns out to be 100 plus 19.2. And so we get the IQ as 119.2. Okay? And that's going to be our answer right here. Okay? An alternative way is just to say, well, z is equal, excuse me, x minus mu over sigma. We have 1.28 is equal to the unknown x minus the mean of 100 mu divided by sigma, which is 15. We're going to solve for x. 15 times 1.28 is equal to x minus 100. And we find that we add 100 to both sides. We get the exact same operation. 100 plus 15 times 1.28, so we get 119.2 is equal to x. Okay? Does that feel okay? All right, well, good. So we're going to encounter a lot of the normal model in the future. Okay, so chapter 6 introduces us to the normal distribution. We're going to encounter it quite a bit in the future, and so you should be comfortable dealing with the normal distribution here. Do we want more practice problems like this, or are we good here? More. Okay. We'll do a couple more. Okay. All right. So I don't know. Okay, so we'll okay, so here's a question. All right, we'll keep it easy, and we'll say we'll say SAT scores. We'll say math or verbal SAT follows normal distribution, mean of 500, standard deviation of 100, and we'll say what is the score of the, we'll say 25th percentile. Okay. What score corresponds to the 25th percentile? All right, let me find our answer choices here. It's fifth week Friday, you guys. So we're like halfway through the quarter. There's still a lot to cover though. Okay, we still have another midterm, we still have another final, or not another final, we still have midterm 2 and the final exam. So, you know, most of you guys did well on the first midterm, but if in case you did poorly on the first midterm, don't feel like all hope is lost. There's still a lot of points out there to turn things around, so we'll be okay. All right, are we doing okay? All right, just a few more seconds to get your clicks in. We'll see. Okay, I'm going to click stop here. And the answer choice is C. On the other one, the answer choice was E. Just make sure. Okay. All right, and so you know, let's take a look. We're going to put 500 in the middle here, and what we want is we want to draw a cutoff line so that the amount over here, so that this amount is 25%. All right. So we go to our table, and we're going to look for the area that's closest to 0.2500. And as we look, we see 0.2514 and 0.2483. Between these two values, I'd say this one is closer, and that corresponds to the row -0.6 and the column 0.07. Okay? So the closest value I can find is 0.2514. Okay? Just want to make sure everyone's okay at this step. All right, and so if our z-score is -0.67, we want to turn this into an SAT score. So we're going to have -0.67 is x minus the mean of 500 divided by 100. Okay, and so that there is our answer choice right here. Just solving for x. Is this okay? All right. All right. Okay. Then I don't know. I feel like we've covered normal distribution okay enough. I'm going to introduce the topic of the binomial distribution, and we'll cover this more in depth on Monday here. Okay. So this is chapter 6. Continuing on, and we're going to talk about the binomial distribution. Okay, and so the binomial distribution we repeat a random experiment, quote-unquote experiment or random trial, n times. Okay, so we do the same thing over and over again n times. Okay. Each time we perform the random trial, we have a probability P of a quote-unquote success. Okay? The label success in our day-to-day is associated with a good thing, and failure is associated with a bad thing. Here in statistics, or as far as the binomial distribution, it just means either something happened or it didn't happen. It's not necessarily a good thing or a bad thing. Okay? So success, and which means there is a 1 minus p probability of quote-unquote failure. Okay? But these are arbitrary labels that don't necessarily mean good or bad. Okay? Each trial is independent of each other. And we are interested in the probability of getting X successes. Okay, and so so simple examples of binomial problems. Okay, I will flip a coin 4 times. Okay, what is the probability that the coin lands heads 3 times? Okay, so in this case, our n is 4. We are repeating the trial 4 times. A quote success is heads. Okay, and then so P is the probability of a success, which is going to be 0.5, and our X, we are interested in seeing X is equal to 3 successes. Is that okay? All right, let's try this out. Let's see if you could identify the N, P, and X in this case. Okay, so we'll say so Steph Curry is a basketball player. Okay, let's just say Steph Curry is it's probably a little bit better than this, but we'll say is a 90% free throw shooter. Okay, meaning every time he takes a free throw, he'll make it 90% of the time, okay? It's probably actually a little bit better than that, but I don't know, he just got into the, 40, 50, 90 club, so good for him. Okay, and then, and we will assume each shot he takes is independent of each other, which may or may not be true, okay? Okay, so let's say in a game, he takes 9 free throws. Okay. What is the probability he makes at least 8 free throws? Okay. So in this case, how many trials are we performing? 9 free throws, right? 9, okay. A success will be defined as him making the shot. Okay, so what is the probability of a success? We're saying 90%, okay? Free throw shooting is 90%, okay? And so, and what is the number of successes X that we are interested in? It says at least 8. So our X will be 8 or 9, okay? So we're gonna go N is 9, P is 0.9, X is 8, or 9, okay? So far, so good? Okay, and this can be generalized to almost any situation here, okay? So we could say, you know, I've got a giant bucket of M&M candies, okay? And we're gonna say it is so big that, so technically when you have a finite population, if you draw one, like let's say I start off with only 10 M&M candies, okay, and like 3 of them are red and 7 are not red, okay. If I draw one piece out, technically, and that one's red, now there's only 2 red left and 7 non-red candies left, right? But we're going to say this thing is so big that any change brought about by pulling things out is not going to affect the remaining probabilities, okay? So we'll say our population is so big that drawing pieces out will have a negligible effect on what remains. Okay? And then so we could say in this giant bucket, we'll say 15% of the pieces are red. Okay? And then we will draw, I don't know, 50 pieces of candy. Okay, we're going to ask, what is the probability you get at least 6 red pieces? Okay, and again, this is a binomial problem in that we are repeating the same thing over and over again. Every time we draw a piece of candy out, that can be treated as a random trial, okay? So we are doing this 50 times. And because we're assuming that the thing is so big and what happens doesn't affect what's remaining, we're going to say that the probability of drawing a red piece is going to stay constant at 15% the whole time. And then x, we are interested in getting 6 or more. So this is going to be 6 red pieces, 7 red pieces, 8 red pieces, all the way up to, we can potentially get 48, 49, or 50 red pieces of candy, right? It's very unlikely, but it is technically possible that every time we randomly draw a piece of candy out, we happen to get a red piece, okay? Getting 50 out of 50 red pieces to be red will be incredibly unlikely, but we have that, okay? So this is just introducing you to the concept of the binomial distribution, where we have to identify NP and X. We'll talk about calculating these probabilities next week, okay? We'll see you guys.